Thanks, Shashanka. Can you hear me in the back? It's okay? All right. So I'll be talking about learning from one continuous stream. And the goal for many people today, post all these improvements we had with deep learning over the last decade, is to build something like a baby, right? In human learning, starting from babies, like Yuki was already saying, we don't need to do much. We just need to get out of the way of the children, just keep them safe, feed them, and they'll just learn, right? So they start from very little. They know very little in the beginning. And a few months later, they develop depth perception and all sorts of things. So initially, it's mostly just observing the environment. They can't move much. It's just standing there. Over time, they start interacting with objects. And eventually, they pick up on language and then really soak up lots of different things that people have learned in the past over the centuries, the years, etc. So this contrasts with powerful modern AI systems where you need first a lot of money to have lots of GPUs, thousands and thousands of GPUs. You need the whole internet, the data from the whole internet, and you need this gigantic, well-paid team that does a lot of data cleanup, but also babysitting experiments, hyperparameter tuning, and so on. So very different settings. And there's also a very big difference in the regimes of the data, right? So Yuki as well was showing these very nice continuous streams that are very different from the type of data that these big AI systems learn from. So on one hand, for a baby, say, or animals and so on, data arrives sequentially. So you need to wait for the data to arrive. It's not there from the start. On the other hand, it's highly multimodal, right? So we have lots of sensors. We have 2 ears, 2 eyes. We have touch, taste, smell. So it's a single stream, but it's very rich. Whereas typically on the internet, it's less rich. It's like images, maybe videos with audio, maybe with text. And finally, a big difference is that the data is very correlated. When you have a single stream, it's boring and it's very, very long. So years, right? For many of us here, 20 years, 30 years, 40 years, and beyond. Whereas on the internet, it's on the order of seconds, usually. So very different regimes. And we know how to do the thing on the right, and we really don't know how to do the thing on the left yet. OK, so I'll cover these 3 differences, starting with one of them, which is if you have a single continuous stream and you have this highly parallel hardware, how do you use that parallelism, and how do you process efficiently this single stream? So there's a common thing between brains and GPUs, which is they're both very, very parallel, right? They have a lot of parallel compute available. And but if you look at a model for processing a video, say a frame level model, what happens is that if the video is arriving sequentially, you can't parallelize too much. You need to process the first layer, and there's some parallelism there, like say convolution. You can parallelize spatially, but then you need to wait for that first layer to finish before you go to the second layer, and then do the second layer before you go to the third, and so on. So it's not really doesn't lend itself to the hardware, to the parallelism of the hardware, because it's very sequential, right? Especially if you have batch size 1. If you can batch things and process 1,000 videos at once, you're fine. But if you have a single stream batch size 1, that's a big problem. So back in ECCV'18, our solution to this was something we called depth parallelization. So the idea is that in the basic image model, your arrows are vertical. So you're processing one layer of a frame, then you pass the activation to the second layer, and so on, and you wait until the end, and then you move on to the next frame. So what we did here is, instead of being vertical, we make them diagonal. Now, if the arrows are diagonal, then obviously you can do all the layers in parallel at once. So lends itself to parallelism. But now you have the challenge that what happens is that you're essentially predicting the future, right? So if you're predicting Y3 in the figure, then you've seen I0. So you're training the model now to be predictive. But you can do parallelism in this case. And this works also because videos are very, very correlated. So, in short time frames, you can predict what's going to happen. If I'm moving here, within a fraction of a second, this is something that is predictable. Okay. Yeah, I have a low quality video back from 18, but the main result is that we could get comparable results to the model without the parallelism, with the latency 6 times smaller. And so after both inference and training, so if you're doing online learning, the backward pass is like a big part of the computation. So we wanted to also parallelize that, and then the idea was to do something very similar. So you do this diagonal arrows both in the forward pass and also in the backward pass. And there's an approximation necessary here, which is, so on the backward pass, you're using the gradients from the previous time step. So there's an approximation, it's not exact, and as you keep going down, you're taking gradients from more and more of the previous frame. But anyway, it's an approximation. We saw that it works. In video, there's a lot of smoothness, and the SGD itself is an approximation. You're approximating, computing the gradient on the whole data set by computing on the batch. This is an additional approximation that allows you, using parallelism to its max on parallel hardware like GPUs when you have a single stream. All right, that's the first thing I wanted to mention related to learning from a single continuous stream. Then the second thing is how to integrate information from many modalities and time as well. As I was saying, like people, we have this one stream, but it's like mega rich, right? So we have ears, eyes, nose, tongue, and we have all these wires coming from everywhere in our body. So like proprioception. So if I close my eyes, I still know where everything in my body is because we have little nerves there telling us position information. So we have this really rich network of sensors throughout our body. And something like a self-driving car can also be put in this position. So they have like Waymo, they have dozens of cameras, dozens of lasers, all kinds of sensors that also need to be integrated. So the question is how to do that. And if you think of the whole body, all these little wires coming from everywhere, it's not like something that we're going to do a convolution over like in a VIT, right? It's not like a square array. It's like a crazy topology of lots of little sensors coming from all over the place. And if you look in the past, what people would do is to do specific convolution, say 1D convolution for audio, 2D convolution for video, and then all kinds of modality-specific encoders for different modalities. And back in 21, we came up with this idea of the perceiver that did away with all of this. So the idea is that you just stack all your modalities into a single array, which we call here byte array. And then, so independently of where they are, so permutationally invariant, so you don't need to do any preprocessing, just stack all the audio, all the video, any other additional sensors you have. And then the idea was to have a latent array, which is small. You can design how small it is. And then you project your inputs into this latent array. This has good efficiency implications because instead of being quadratic in the number of inputs, so it depends now on the size of your latent array. And then what we did was to have self-attention in this latent array and iterate a few times. So that was the perceiver, the initial perceiver, which was just for classification. We could also share weights between every iteration, so it is a bit like a recurrent model. And then we did classification with it. Afterwards, the next year, we expanded this into having a symmetric encoder and decoder. So we could now also have arbitrary outputs on the decoding side. And we showed that, even we didn't have any baked-in priors about the structure of the data. We could even do very accurate optical flow, which requires very detailed understanding of a video. And so this summer I was in Berkeley, and something completely unrelated. There was a talk by David Chalmers, who's the leading philosopher on consciousness, and the topic was, quite, not a safe topic, whether LLMs are conscious. And his answer was that they weren't yet, but they could be in the future. And he had a whole argument about how biology isn't necessary, and that LLMs already have sensory multimodal processes at the embodiment and some world model, but they lack robust self-models, recurrence, global workspace, and unified agency, but these are coming, maybe. And he cited a paper that says that the perceiver architecture is a functional global workspace. So it's one of the things that may help models become conscious. Okay, a bit out of scope here, but it was fun to have this reference. So I just mentioned it here. So David Chalmers is the one little person there on that side. Okay, and we have some new work in this area as well called MOOC, moving off grid, but accepted to NeurIPS. It's like a perceiver. It has this latent array, attends to the inputs, and does this cross attention to the code as well. And so the idea there is that these perceiver-like models, we also call them off-the-grid models, because each feature vector, this latent space, is not attached directly to a particular patch. So if you have a VIT, at the output of a VIT, you have this grid of features. Each of them represents a patch. So if you're moving the camera around, all these feature vectors are changing, right? So whereas with the perceiver, the hope is that the feature vectors are from the input space. So if you move the camera around, the hope is that these features are persistent. So you move the camera around, and the features don't change much. So that was a hope. And what you observe is that if you train to predict the next frame in a recurrent way, you get some of these properties. So if you look at the latents, they seem to latch on to particular features in the scene rather than just describing individual patches. So here we're taking like some argmax latent for a particular patch, and you see that it follows around scene content. All right. Okay, so then finally, problem 3, how to make the model learn, right? So what happens is that if you have a sequential stream, that data is arriving sequentially, and it's very boring. What happens is that the consecutive batches, you look at the gradients, they're very correlated. So on the left, I'm showing these very tall bars. It means that the consecutive gradients between batches, they have very correlated gradients. They're very similar. Whereas if you have IID batches, for example, like the walking tours paper that Yuki was saying, so it's a single video, but it's treated like a data set, right? So it's shuffled, big batches. So you have the gradients that are very decorrelated. So that's the assumption that SGD makes, and that makes everything we do work. So if you see on the right, if you have these IID batches, the semantic segmentation accuracy in this case is going up. Whereas if you have a continuous stream, it's not learning, it's just staying there stuck. So there's a lot of research required to make this work. And basically, the problem is that SGD, while very robust, assumes that the batches are random. So that's the underlying assumption of SGD. So the problem is not that the batch size is 1. So Jan LeCun likes batch size 1, for example, and he says that friends don't let friends use mini batches larger than 32. There are papers showing that training SCD with batch size 1 is actually pretty good for generalization. So batch size 1 isn't really the problem. That's fine. The problem is just this stream, this normal stream we see is very boring. So that's the big problem compared to, say, ImageNet or Kinetics or IID datasets. Right, so this brings us to this paper we had in CVPR last year, where we tried to look a little bit into this. There's very little work on it, so we're just really doing the basic groundwork on seeing what happens if you try to train from a single continuous video stream. Okay, so first problem, there's no data. There's no data sets with very long continuous streams, not on the order of or months or anything. There's like Ego4D, it has videos that are up to 2 hours, median length like 9 minutes or so. And we also used ScanNet, which is even shorter. It's like up to 6 minutes or so. So these two data sets. We put in this case Ego for the stream for ScanNet, just stack the video there. For up to 24 hours, because we train on 24 hours. So you can get a very good data set for this. Probably we'll do it in future work. And yeah, this is how the data looks like compared to IID sample clips from it, and from like the correlated stream, whereas we concatenate the videos as they are in frames. present, which makes sense for something like semantic segmentation or depth estimation. So, we used these tasks for evaluation, but we could also use representation learning as evaluation. We didn't use it, but there's a paper, probably the only other paper that focuses on this exact problem from Abhinav Gupta's team that did representation learning type of evaluation. Here, we just predicted the future. And we evaluate two different things. In-stream adaptation, which means, so I'm here and I'm fitting a model to this scene. So I know I have a microphone in front of me. I have these people here. So this is like how well you can fit to the stream you're in, and that there's continuous learning happening. And we're also testing for out-of-stream generalization, in which we just bring that model that is being trained on one stream, we bring it to another stream, we don't adapt the weights, and we just see if it can generalize to new scenes. So we have these two things that we want to maximize. And so as I was saying, this is like very early stage work. Basically, we got some results on two things, optimization and pre-training. And one of the things we learned is that non-standard optimization settings help. So we did a big sweep over different optimizers and found that RMS prop was the best by a good margin. And then we looked, okay, so what makes RMS prop so much better than Adam? And we found that Adam has this momentum term that is hurting in this case. And we tried to vary, to lower the momentum from the default 0.9 up to 0, and it kind of kept improving. So I guess the interpretation is that, so momentum is just trying to stabilize the gradient in some sense, right? To make it like more or less constant in time. But if your data is already like very correlated, you don't need it. In fact, it's hurting. You already have momentum because the data is very, has a similar gradient. So that's one thing. And so another thing we try is to vary how often to update the weights. So you can update every step, or you can accumulate gradients for a few steps and then update the weights to the particular stream you're in. So it's, the video is correlated. So if the microphone is here now, next second it will be. So you can really overfit to that scene. So the more you update the weights more frequently, the better you do. On the other hand, if you update too frequently, then when you go and try to generalize in the other stream where you're not fitting the weights to, it hurts generalization. So if you update very, very free, 16 steps or so. So there's this trade-off between adapting to the stream you're in and generalizing, learning generalizable features. And in practice, what we did was to set it to 16. So we update the weights every 16 steps or so. And let me see. Yeah, I have some visualization here. What this shows is in out-of-stream generalization, as the model is traversing this stream where it's learning to, you see that it's producing vastly different predictions. It should be brown, but depending what the model is seeing, it's like just predicting very different things, right? So this is like when you have this steps of one or so. So you're updating the weights very frequently. It's not generalizing well. It's just like hallucinating things when you take it out of the current stream. Whereas if you update every 16 or 64 steps, then it's generalizing better. It's getting better, closer to the brown color that it should be predicting in a out-of-stream setting. Okay, then this is a self-supervised learning workshop. So does self-supervised pre-training help? So you start the model with some initial weights. Will it do better? Will it learn more after one day of online training? And for that, we compare three things. So no pre-training, image-based pre-training like MAE or classification, and also video-based pre-training. And for video-based pre-training, we tried three different approaches. They're all looking at 4 frames and predicting 4 frames in the future with some delta. And we tried just vanilla. Future prediction is just seeing some frames and predicting future frames. Or future prediction in which you see the current frames, but you overlay some patches from the future. So you can see that there's some 4 or 6 little patches that don't belong there in the input. So those are patches from the future. So giving some guidance and reducing a little bit the entropy. And the harder task, which is mask future prediction, where you mask most of the pixels and you just keep a few patches around, and now the model needs to predict the future. And I can just show, I think I'll just pause it here just to get a feel. So the inputs are on the top for a guided feature prediction. You can see that there's some weird patch here. So it's a guiding patch. These are the predictions, which are sharp around here because it has that guiding patch. And this is the target. This is for mass feature prediction. It's a very hard task. It's harder than image mass prediction because you need to, remove that gray stuff from the image, but also you need to put it in the future. So you predict in the future, right? And the vanilla feature prediction is just predicting the future, just a simple one. And for us, it worked best guided feature prediction. And you can see that pre-training matters. So if you don't have a pre-trained checkpoint, performance is worse. For example, segmentation gets low performance compared to either using classification or MAE or best case, a video pre-training approach. So video self-supervised learning helping here. Then we went and tried, after we did these improvements on the optimizer and on the pre-training, we tried to go back and compare to IID training. So we have two settings here. One is what we call standard deep learning. It's a baseline, uses Adam, updating weights after every batch, in this case, after each video chunk. We use the ImageNet MAE checkpoint, and we use batch size 1, so trying to set that the same, batch size 1 in both cases. And then what we call the baby learning approach, where we use RMS prop. We update weights after every 16 video chunks, use the Kinetics guided feature prediction, and again, same setting, batch size 1. And what we observed is that if you use the standard deep learning approach with a continuous stream, so here in purple, the model just doesn't train, right? So that's what I was showing in the beginning. If you have these very correlative gradients, there's no training happening. If you do IID standard deep learning, the blue one, it trains normally, but in this case, with our settings, the green one curve, so these baby learning settings with the video pre-training and the changes in the optimizer, we actually do better than the baseline here. This is in stream, so adapting to the current video. Now, if you look out of stream, again, the standard deep learning in the continuous setting just doesn't train at all. It's flat. And the baby learning approach roughly matches the standard deep learning one, or slightly better, actually. Now, you can ask, what if you go to this baby learning setting, but now you make the data IID, and that's like a kind of a negative result? It improves a lot, right? So IID is still helping load. I'm very glad the paper got accepted despite this. It's good to have some, clear gap every once in a while in a paper. But the truth is, this is a very hard problem. We really don't know yet how to solve it. We need new ideas. We're still operating with SGD, which is not meant to work in this IID, in non-IID setting. So yeah, easy to make progress for sure if people put effort into it. Yeah, but here it seems like the improved pre-training is helping everything, more or less. Right. In conclusion, I think we're just scratching the surface of single stream learning, and much, if not all, of research there to do. It's cheap. You don't need a lot of GPUs to do this, so anyone can do it from their homes. Needs great ideas, and really, I mean, IID shouldn't help, right? Like, you're destroying a lot of structure in the data. You have these richly structured videos, and you're just like shuffling them. And you're just doing this because SGD is the current thing that works. We don't have anything better yet, but eventually we'll need something else that can deal with these very long streams, right? So if you want to learn about night and day, night follows day, we won't be able to do it from shuffle batches. This is lost. If you want to learn about the seasons, years, and even shorter scale things, there's a lot that in order to learn, we need to go beyond shuffled data. I think it's the future. It's very risky, so great for academia. You have job safety in academia. So yeah, I think everybody should be working on this. And it goes back to Turing's seminal work on AI, where he was saying, instead of trying to produce a program to simulate the adult mind, that's more or less what we're trying to do with the GPT-4, Gemini, trying to build from scratch like an adult mind. But it's expensive and it's a lot of work. And not as scientifically stimulating as the alternative. So what Turing was saying, why not rather try to produce one which simulates the child? If this was then subjected to an appropriate course of education when would obtain the adult brain. So yeah, that's in conclusion, for time is precious. Okay. Any questions? Yep, question. Hey. That's a very good question. I don't think you really need it. Like for most scenarios, it's mostly like if you want to do something like very cheap in the future that goes beyond what we have now and keeps on improving rather than being limited by the internet or what's on the internet now. Yeah, I think it's mostly like at this point a scientific problem, but one that I think will unlock many things. It will make anyone able to build a GPT-4 style model or beyond from their homes by just taking the model to school or taking the model to watch TV or the cinema. People will be able to, everyone train their own genius level AI model eventually. So, but yeah, maybe not super useful tomorrow. Maybe for self-driving. We have a car deployed in, so it needs to learn what are the good roads, the 3D model of that city. In that case, I think it makes sense to continuously learn rather than have the company with a self-driving car go and map every individual city. So maybe there would be an early step. Yeah.
Thank you. I'm wondering what's missing to, is it just the data that's missing, like analytics? Is that the only thing?
No, I think everything's missing. So the data, that's one thing that's probably the easiest, but also like the algorithm, like SG